me know if you're having trouble understanding or hearing. I'm using a new tablet for this. Hopefully it makes the handwriting better. But then I'm sure it'll come with its own technical issues. So let's start with a summary of what we did last time. Last time we were interested in finding the stationary values of a functional. And a functional is basically an integral. So let's say we have integral I of some function L. And let's use Q's and T's. So the function L will depend on Q1 through to Qn, Q1 dot through to Qn dot, and T. And we want to find the functions Q1 to Qn that make this integral stationary. And so what we want Q1 of T all the way to Qn of T. Okay, and so these are functions, and for a mechanics problem, those functions are, for example, the generalized coordinates. And if we could describe the generalized coordinates as a function of time, then we've described the system. And we'll see in classical mechanics that there's a theorem that tells us that the generalized coordinates and some function of them, when you take the integral, it has to be stationary, and that determines the propagation of the system. And so when we looked at the variation of delta I, we found the Euler-Lagrange equation for each function Qi of T. And the Euler-Lagrange equation was that d by dt of di L by di Qi dot minus di L by di Qi equal to 0. And that's a very important equation. So when we derived this equation, we were allowed to vary all the Qi's independently, right? At one point, the integral depended on delta Qi, and all the delta Qi's could be varied independently. And so this term that's in the box here, the Euler-Lagrange equation, had to be identically 0, since the delta Qi's could take arbitrary values. And that's the argument that we made. Now, if you remember, when we looked at stationary values of functions subject to constraints, the different variables were not free to vary independently of each other because some constraint had to be satisfied. And so we can do the same thing here when we're talking about the stationary value of an integral subject to constraints. And so we'll start from there today. So the stationary value of an integral subject to constraints. So we have our function L of Q1 to Qn, Q1 dot to Qn dot, and T. we want the stationary value of the integral of L subject to, let's say, K constraints. And those K constraints we can write as K equations of the form F1 of Q1 to Qn equals 0, F2 of Q1 to Qn equals 0, all the way to Fk of Q1 Qn equals 0. Okay? So these constraint equations are what we called earlier holonomic constraints. They are constraints between the variables. So note that they're not constraints between the speeds. So they're not constraints on the Qi dots. They're constraints on the Qis. Okay. So these functions are all 0. And that's how you write the constraint. And so let's consider, before we move on, the variations of those constraints. So for example, delta F1 is equal to di F1 by di Q1 delta Q1 plus di F2 by di, plus di F1, sorry. By di Q2 delta Q2, etc., plus di F1 by di Qn delta Qn. And then similarly, all the way down to delta Fk, that's di Fk by di Q1 delta Q1 plus, etc., di Fk by di Qn delta Qn. So let's construct a new function. And let's call this I bar, and that's equal to I plus lambda 1 F1 plus lambda 2 F2, etc. Oh, sorry, that should be an L instead of an I at the beginning. I want the integral of this. So let's call that L bar instead of I bar. So now we want the integral. So I bar, let's call that the integral of L bar between the same limits. And so that's going to be our original integral L, or I. That's the integral of A of B of L dt plus the integral of A to B of, I'm just going to write it as a sum over J lambda J Fj. Right, where this sum term here is the lambda 1 F1 plus lambda 2 F2, etc. Now, of course, we're going to take the variation of this. So the first term is going to be the variation of L dt plus second term, which will be the sum over J. So J goes from 1 to K of the variation delta of the lambda J Fj. And then I guess I forgot the dt at the top as well. So last time, we already handled the first term, the delta L. We found that we could write it as the integral a to b of d by dt of di L. Well, I guess this is going to be a sum now. Let me be more explicit. Let's put the sum term in front. It's going to be the sum, and this is I equals 1 to n of d by dt di L by di qi dot minus di L by di qi times delta qi. Remember, we were able to do this integration by parts, and that allowed us to change the delta L into this form here. That's ultimately what gave us the Euler-Lagrange equation. But in this case, we keep it in, and there's going to be one of these for each q, right? If you take the variation of delta L, there's a di L by di q1, a di L by di q2, etc. And then there's a di L by di q1 dot, and a di L by di q2 dot, etc. You can group all the q1s with the q1 dots, and then you can get this equation here, and it'll be summed over I. Okay, so that's the first term. And then the second term is going to be of the form that we already wrote. Except now that we're going to expand this delta lambda j fj, that term there, the lambda j is a constant, right? So that's the same as lambda j delta fj. All right, so let's just write it that way first. So it's the sum of j equals 1 to k lambda j delta fj. And so what was delta fj? Delta fj is the sum from I equals 1 to n of di fj by di qi delta qi. Right? That is just what we wrote out at the top of the page here. Where you have delta f1, for example, is the sum of the di f1s by di qi times delta qi. Right? So, okay, let me write it out explicitly one more time. I'm doing this a bit more explicitly than in the notes. So the first term is our Euler-Lagrange equation term. And then the second term, so we have first the sum over the j's equals 1 to k lambda j, and then the delta fj we can write as the sum over I 1 to n di fj by di qi delta qi. So that's starting to look a little bit scary. So you will agree with me that I can interchange the order of the sums, right? So the second term here, so I'm going to rewrite the first term, it's the same. And the second term, keep forgetting the limits of the integral and the dt at the end. And there's also a delta qi here. So if I rewrite the second term, just interchanging the order of the sums, one to n, and I have the sum of j equals 1 to k, lambda j di f j by di qi delta qi. So that's dt at the end. Okay? So this sum, what did I do? Okay. This sum term over I is common to both sides of the integral, right? So let's rewrite the whole integral with only one sum over I for both terms. So I have the integral from a to b. The sum of I equals 1 to n. The first term is d by dt of di L by di qi dot minus di L by di qi. Let me put an even bigger bracket at the start of the sum here. And then that's plus this term, the second term, and that has a sum of j equals 1 to k lambda j di fj by di qi, close the big bracket, delta qi, because each term is a sum over I, so both terms from the integral on the line above have a sum over I, something times a delta qi, right? So the delta qi was common to both. And then there's a dt. Okay? So the term that's in the giant brackets, there's one of those terms for each I, right? So now let me explicitly write out that term. So I'll write out the sum over j's for some value I. Well, actually, let's do it for, well, let's do it in general for value I, and then we'll write it out explicitly. So for some value I, I'll write out the integrand. The integrand is d by dt of di L by di qi dot minus di L by di qi, and then it's plus lambda 1 times di f1 by di qi plus lambda 2 di f2 by di qi plus etc. lambda k di fk by di qi. Right? So that's the term that multiplies delta Qi, where all I've done here is expand the sum over the lambdas and f's. All right, so what we did earlier when we didn't have the constraint equations, we only had this first term here in brackets. And we said that since the Qi's are independent, the integrand has to be 0 regardless of the value of Qi that we choose. And so that means that the term in brackets has to be 0, and that gives us the Euler-Lagrange equation. That's not true anymore now because we can't vary the Q's independently because of the constraint equation. If you vary one of the Q's, another one of the Q's is going to have to change as well, dependently. So, of course, we're using the method of Lagrange multipliers, where we've introduced these k values of lambda without specifying them. So we can now specify them so that the last k equations are identically 0. So we choose the lambda 1 through lambda k such that this equation here is equal to 0 for Qn, Qn minus 1, all the way to Qn minus k. Right? So now we have the k equations that force these last k terms to be identically 0. So we've effectively eliminated the last k generalized coordinates. What that means is that the first n minus k coordinates can now be varied independently. And if those can be varied independently, then the integrand must be 0. But the integrand, of course, for the first n minus k variables looks exactly the same. That's the whole point of the Lagrange multipliers. And so what we get is for all values of I from 0 to n, not just n minus k, we get that this equation must equal 0. And so what we find is for all I, and I'm literally just rewriting the same equation, we have, and I'm going to move one term to the other side, we have d by dt of di L by di Qi dot minus di L by di Qi equals, on the other side, minus the sum of j equals 1 to k di F j by di Qi times lambda j. It's probably prettier if I put the lambda j in front. Let me just do that. And so that is the same thing as the Euler-Lagrange equation when there are constraints between the coordinates. Okay? And then this minus term here that we have, it's arbitrary, right? It can be a plus. And that just means that L bar was L minus lambda 1 F1 minus lambda 2 F2 minus lambda k at k. Okay. But we can leave it in. And so this is a very obscure, again. It's just the math of finding the stationary value of an integral subject to the constraint given by the f equations. We'll, however, see as we do classical mechanics, starting in the next chapter, that this term on the right, these constraints, are actually related to the forces. So for example, if we go back to our example of two masses held by a rigid rod, it's a constraint from the rod that those two masses cannot move with respect to each other. So that rod provides a constraint on the coordinates of those two masses. And we'll find out that this term here, lambda di f j by di q I, where fj is the equation that relates the distance between the two masses, we'll find out that this term actually gives us the force of tension that's in the rod. And so it turns out to be quite beautiful mathematically, that this rather abstract math gives you back the concepts that you had from Newtonian physics. So that's the end of our section on the calculus of variations. Do we have any questions on that? Okay, so now we'll start and go back to classical mechanics, and we will keep these results from the calculus of variation in the back of your mind because we will use them again. And by the end of the course, it will be second nature to do these variations of integrals. At this point, I realize that they feel like they're kind of arbitrary rules, but as we do more of them, we'll see that there's a consistency in them. So we're going to start what we're calling chapter 3 here. And that's the principle of virtual work. And D'Alembert's principle. And so, well, I'll remind you that the assignment is due tomorrow, but in the assignment you were supposed to do the double pendulum using Newton's laws, and then you probably found that it was rather annoying mathematically. And so the whole goal of this course is to do classical mechanics in a new way that's actually much more straightforward and much more general. And we'll see at the end of the course that there's actually a deep connection with the laws of quantum mechanics. So we'll start with the principle of virtual work. Just like when you did first year mechanics, you did Newtonian mechanics, you first started with static problem. What's the balance of the forces so that the thing doesn't move, and then you moved on to letting the thing move and finding its acceleration. And we'll do very much the same progress here, where we first consider problems of statics. So one of the big simplifications in classical mechanics, or this so-called analytic mechanics, is that we can ignore a lot of things that are typically not very useful. Specifically, I mean what we call internal forces. So let me just make a comment that in analytic mechanics, we distinguish between internal and external forces. And put them in quotation marks for now. And we can usually ignore the internal forces. So, for example, if you have two masses connected by a rod, and let's say gravity is acting on them, gravity we would call an external force. Whereas the tension that's in the rod that prevents the masses from moving away from each other, we call that T. We would call that an internal force. And the idea here in analytic mechanics is that the motion of the two masses does not depend on the tension of the rod, right? If you're interested in only describing where those two masses are, conceptually, it only depends on gravity. It shouldn't depend on the tension between the two. However, if you want to solve for the motion of the two masses using Newton's second law, you have to actually include in the sum of the forces the tension on each mass. And so the beauty of these analytic mechanics is that we'll find that this internal forces are almost always ignorable. And in fact, we will just develop the rest of the framework by ignoring them completely. So that's sort of the introductory idea. And now let's see how this is implemented. So let's start by discussing virtual work. Yes, there's an opportunity to make lots of jokes about people doing virtual work. But in classical mechanics, the virtual work of a force I is denoted by delta Wi. So we use a capital W for work. And it's the scalar product of Fi dotted with delta Ri. Okay? So what is everything here? Well, Wi, or delta Wi, is called the virtual work. Of the force Fi. The force Fi is just the same thing that you would have in Newtonian physics. And then delta Ri is what we call a virtual displacement. So what is a virtual displacement? It's a displacement without the passage of time we actually already mentioned this in the introduction to the variational calculus. So virtual displacement, it's not dr, where dr by dt is how r changes as a function of t. So it's not consistent necessarily with the passage of time. You can choose a delta r that's in the same direction as dr, as r evolves with time, but it doesn't have to be. It could go backwards, for example. And then the other point about the displacement, the virtual displacement, is it's a displacement for lack of a better word, I'm going to say it's a displacement that's in harmony with the constraints. And it's also a reversible displacement. And reversible in the sense that it is still in harmony with the constraints. So what does in harmony with the constraints mean? It means that, say, for example, if we have our two masses that are connected by a rod, and I want to consider the virtual displacement, well, let's say actually that one rod is fixed, to simplify things. The rod is rigid, and let's say it can rotate. Then a virtual displacement has to be in harmony with the constraints. So what that means is, if I want to consider a virtual displacement of this mass, because of the constraint of the rod, this delta r would be forbidden. The mass is not allowed to move in a direction parallel to the rod, or have any motion parallel to the rod. So this is not permitted. It's not in harmony with the constraints. So basically this mass here can only have virtual displacements that are perpendicular to the rod. That says delta r is okay. All right, so that's what it means for a virtual displacement that's in harmony with the constraints. Now, if this is, for example, in the vertical plane, right, the mass would go downwards. And so you're allowed to choose a delta r that goes upwards, so against gravity, because it's okay with the constraints, but it doesn't have to be in the same direction that it would evolve with time. And that's what makes it a virtual displacement, not a total displacement. So it's not a dr, it's a delta r. All right. The other example is, for example, if you have a block sitting on a surface, right? So you have some normal force. On the block. The only allowed virtual displacements of the block are parallel to the surface. So by definition, a virtual displacement cannot be parallel to a normal force, because a normal force is by definition a force of contact between two things, and you can't move while still satisfying the constraints inside one of the surfaces. Okay? And so this, it'll be more clear when we do more examples. But that's the general idea, and those conditions that I gave you are the conditions for virtual displacement. So the principle of virtual work is that the sum of all the virtual works on the system is equal to 0, and that implies that the system is in static equilibrium. So that is similar to the Newtonian case where the sum of the forces must equal 0 to get a static equilibrium. But there's a big difference between these two equations. The principle of virtual work is a scalar equation. The sum of the forces in Newton's law is a vector equation. And so that's 3 different equations if you're in Cartesian coordinates. So of course the whole point of this analytic mechanics is that we'll do away with vectors and we can do everything with scalars. And so this principle of virtual work is truly a novel way of doing things because it allows us to use only scalars and so only one equation to determine static equilibrium. Whereas if you were doing Newton's laws, you'd have to have a sum of the forces in the x, y, and z directions and solve all of those to figure out, what the equilibrium condition is. So it is really a different way of doing things, but conceptually, since if you've never done this, it's a bit strange, but you'll get used to it. So let's do example 3.1. There's a bit of a typo in the notes on the way it's explained, the example. It says the work done by a massless bar that holds 2 masses together is workless. But it doesn't mean so much. It's more like the force, all the forces on the rods from the internal forces are worthless. So let's do the example of the rod. So we have 2 masses which we'll call M1 and M2. And they're connected by a rigid rod, right, of length L. And they're otherwise free to move in space. So let's think about it a little bit in terms of Newtonian mechanics. So the rods, the balls on them, are going to have a force on them from the rod, right? So let's just very generally say that the force on M1 is F1, and the force on M2 is F2. All right. And we know from Newton's third law that F1 vector is minus F2 vector. Right? The forces are equal and opposite. Let's draw some virtual displacements. So none of the masses are constrained in the plane. They're constrained with respect to each other, but in principle, if I take mass M1, I can move it in any direction that I want. Now, if I move mass M1, the system at mass M2 has to move in the same direction. So let's call that delta R2 for now. So a virtual displacement that's in harmony with the constraints, if I move M1, then M2 has to move in the same direction. Okay? So our constraint equation of having this rod, if I specify each mass by some position vector r, then the constraint equation is that the distance between the two masses remain fixed. And so that's r2 vector minus r1 vector. The length of that has to be equal to L. So if I take the variation of this equation, delta L is 0. L is a constant, so if you vary the position of one of the masses, L doesn't vary, right? And so what we find is that delta R2 must equal delta R1 vectors. And that's what I sketched in the diagram. But now I prove it to you mathematically. Maybe I should have proven it to you mathematically before sketching it in the diagram. So let's calculate the total virtual work. So the total virtual work, the sum of the delta Wi, that is the sum of the F1 dotted with delta R1 vector. Well, I guess I don't need to write the sum term if I'm actually writing the terms out. That's F1 delta R1 plus F2 dotted with delta R2. Now, we found that because of Newton's third law, F1 vector is equal to minus F2 vector, right? So that's the same as saying F1 dotted with delta R1 vector minus F1 dotted with delta R2 vector. Oops. And so now we have delta R1 and delta R2 equal to each other. And so what we have is F1 dotted with delta R1 minus F2 dotted with delta R2 equal to 0. Oops. Well, it's pretty obviously equal to 0, right? That was just the first time. It's F1 dot delta R1 minus F1 dot delta R1. And that's equal to 0. And so in fact, this virtual work done by the only forces in the system, which are the F's, gave us 0. So it's identically 0. So it really doesn't tell us anything of whether the system is in static equilibrium or not. So what was the point of doing this? Well, the point of doing this was to show you that in almost all cases, the work done by internal forces, so the F's are the tensions in the rod, right? In almost all cases, the work done, the virtual work done by internal forces is 0. And since it's identically 0, it can usually be ignored. And this is what forms the basis for the statement I made earlier of us being able to ignore these internal forces. So let's go back and write that out explicitly. So if we have a system, the sum of the delta Wi's is 0 means that we have static equilibrium. Now the sum of the delta Wi's, let's break this up into a sum of external forces. So I'll put an upper index E dotted with the delta Ri's, plus a separate sum of Fi, and I'll put a capital I to indicate internal forces dotted with delta. I guess I should use a different index, so I'll call them Fj's and Rj's. There might not necessarily be the same number of external forces as internal forces, right? And so Fe I is an external force. And Fj, capital I, is the internal force. And in general, as we just saw an example, the virtual work of the internal forces is equal to 0 because of the constraint equations. If the forces are related to constraints, effectively that's what results in the virtual work of those forces being 0. And that's very useful. When I say in general, I mean often, I guess. Mathematically, those are different words. But by often, I mean almost always. Okay? And so if this is true, if the work done by the internal forces is equal to 0, we call the constraints associated with the Fi's workless constraints. And of course, we'll limit ourselves to most systems where the constraints are indeed workless. So again, for example, example 3.2, you have a block on a surface. The constraint is that the block cannot go through the surface. Which means that there exists a normal force. This E pointing the wrong way means there exists. Okay, so on this block here, then you would have some normal force, as we already discussed earlier, delta n. All of the virtual displacements that are allowed are by definition perpendicular to n. So now the dot product, which is what comes into the virtual work of two vectors that are perpendicular to each other, is of course 0. And so you automatically get that n dotted with delta r. So the virtual work of n is always 0 for the allowed delta r. Okay. And so I remind you that this is a big advantage compared to Newton's second law, because in Newton's second law, you have to take into account the normal force and the tension in the rod and the tensions and strains and all that when you do the sum of the forces. With this new system of virtual work, you don't need to. How far am I? All right, start a new page. So let's do a little bit more of the math, and then we will do some examples of real static problems where you can actually see how to apply this. Because even for me, when I just went through this, I didn't know. It takes a little bit of practice to apply. The question from Lou, which I just saw, which was from half an hour ago, I'm sorry, is the assignment is due tomorrow, I believe. Or sorry, yeah, okay, yeah, no, Friday. Yes, I didn't mean to say tomorrow. Tomorrow's Thursday. Feels like Thursday. No, the assignment is due Friday. Sorry about that. Okay, so let's talk about generalized forces. And then we'll do some real problems where we can apply all of this. So remember, the total virtual work, delta Wi, was equal to the sum of the external forces plus the sum of the internal forces. And these internal forces are often equal to 0. Oops. We will ignore them from now on. I gave you two examples of pretty typical internal forces: tension in a rod or a string, and a normal force. Those are like the majority of constraints. And we just saw that both of them lead to no work, or no virtual work, sorry. So we'll start by assuming from now on that delta Wi is equal to the sum of, I keep forgetting vectors everywhere, of the external forces dotted with the virtual displacements. Okay? And the principle of virtual work will apply. It tells us that when this is equal to 0, then static equilibrium. So I introduced the term generalized forces. Recall, if we have n degrees of freedom, we can have n generalized coordinates q1 to qn. That means that we can write the vector r, any vector r, so let's call it vector ri, as a function ri of q1, q2, qn, and in principle it could also depend on t. So in this principle of virtual work, right, we have the delta r. But we want to change this to generalized coordinates, so we want delta r in terms of the generalized coordinates. So delta r, I, is equal to di ri by di q1 delta q1 plus di r1 by di q2 delta q2, etc. di ri, every time it's a vector I, by di qn delta qn. And you can see what we're doing here. What we're doing is we're getting rid of the r's, which are vectors, in favor of the q's, which are not vectors. Because that's the initial promise, is that we won't care about vectors eventually. And so we can write that a little bit more elegantly as the sum over I, if I made this I, then that's going to be the sum over j of delta ri by di qj delta qj. Right, that's delta ri. Let's put that into our virtual work sum. So the sum of the delta wi's, let's go I from 1 to n, that's equal to the sum of I equals 1 to n of the external force I, dotted with the delta ri, which is the sum that we just wrote out, so it's a sum over j's, di ri by di qj delta qj. Now let's just rewrite this by switching around the sums. So I'm going to put the sum over j out first. Oh, I'm sorry. I should distinguish. The i's don't necessarily sum up to the same number as the j's, right? So we've been using little n as a number of generalized coordinates. So j should go from 1 to n. And let's say that the forces, that there are maybe, what's a good number? N. No, big N is what's in the notes. So there are n generalized external force, or n external forces, right? So the sums over the index I are up to n, not little, or up to capital N, not little n. So the sum of the delta wi's, it goes, there's n of them here as well. Inverting the terms in the sum, so it's the sum from j equals 1 to little n. And then I'll write a bracket here. of the sum over I and the guy goes from 1 to big N, Fi external force dotted with di r I vector divided by di qj delta qj. Let me introduce what we call the generalized force. And I'm going to label it with a capital Q and index J. And I'm going to define that to be the term in the brackets. So that's the sum over all the forces, I equals 1 to big N, of Fi external dotted with di r I vector by di q j. Okay? I'm just defining this new thing, which I'm calling the generalized force. That means that our virtual work, the sum of I go 1 to n of the delta Wi is now equal to the sum of j equals 1 to n, little n, of big Qj delta Qj. And note that we don't have any more vectors now, right? Because we gobbled up the vector product or the dot product between vectors in the definition of Qj, so that now our total virtual work appears to be the sum of the capital Qj's with multiplied by the virtual displacements delta little qj's. Now you could almost think of this as a dot product. Oops. Of some big vector Q and some other vector delta little q. Right? If you take the qj's to be the components of some vector q, so it has n components, where n is the numbers of degrees of freedom, and you do the same thing for the delta qj's and make a vector delta q, then this virtual work is like the dot product of these two vectors. And so remember now, if the principle of virtual work tells us that if the total virtual work is 0, we have static equilibrium. And so let's think about what that means. Let's add a page. So if the total delta Wi equals 0, that means that the sum of the qj delta qj equals 0. However, the delta qj are generalized coordinates. That means that they are independent. That means, for example, that delta qi does not depend on delta qj, for example. So it means we can vary the qi's independently from each other. It's back to the same concept of we were minimizing or finding the stationary value of a function with no constraints. That means we could modify all the delta q's independently. Same thing when we vary the delta q's independently. Same thing when we did the integral. There was no constraints, so proper generalized coordinates, then the delta qi's are independent of each other and they can be varied independently. So if this sum is equal to 0, the sum of qj delta qj, independent of our choices of delta qj, the principle of virtual work tells us that for static equilibrium, the qj's are 0 for all j. And so physically, the meaning of these qj's, they're called generalized forces, but they may not have units of force in the sense that they're newtons, meters per second squared times mass. So they might have different dimensions than actual force, but the concept is if they're all 0, so none of these generalized forces are applied on the system is in static equilibrium. So it starts to become a very deep and abstract understanding of mechanics. But you can sort of think of these qj's as forces in the generalized coordinate directions. And the generalized coordinates can be weird, right? They don't necessarily have to be the Cartesian x, y, and z. Ultimately, can be. They can be a combination of the coordinates or some angles. Specifically, if they're angles, then what does it mean for a force to be in the direction of an angle? Well, that brings us to the concept of torques. Torques are like forces, but that move in the direction of an angle. And then as we'll see in the examples, these generalized forces are sometimes forces and they're sometimes torques. And sometimes they could be something way more abstract. So let me end today by writing out a procedure for solving problems using the principle of virtual work. And then next Monday, we'll begin with a summary, and then we'll solve some of these problems using virtual work. And then you will eventually be convinced that it's less strenuous work and more general than using Newton's laws. So I'm going to write sort of a procedure for how to solve static problems. Using the principle of virtual work, PVW. So step 1 is to determine the unconstrained number of degrees of freedom. So if you have one particle by itself in three-dimensional space, that number is 3. Step 2 is to determine the number of holonomic constraints. So remember, a holonomic constraint is a constraint between coordinates, so not involving their speed. So it allows you effectively to eliminate one coordinate in terms of the others. So then step 3 is to choose generalized coordinates and write out the transformations, the coordinate transformations. Step 4 is to identify the forces that can perform virtual work so this forces that can perform virtual work, internal forces, as we saw, generally cannot perform virtual work. And then sometimes there are forces that are applied on locations that can't undergo virtual displacement, like if you have a pendulum that's swinging, and the pendulum is a rod, not a string, then the point of rotation cannot move. So even though there are forces on that point, the point itself is not allowed to have any virtual displacement that's in harmony with the constraint that it's a fixed point. And so no matter what forces are applied there, even if somebody's pushing on top of the pendulum with a finger, that has no effect on the pendulum because that point can have no virtual displacement. Step 5, right at the bottom of the page here. Step 5 is to write out the virtual displacement. Oops. At points where the forces act. Step 6 is to write out, so now you have the virtual displacements and you have the forces, and the virtual displacements you've written in terms of the generalized coordinates, so you can now write out the total virtual work. Which is the sum of the delta WIs. Step 7 is to set that virtual work equal to 0. And we saw that alternatively, you can calculate the generalized forces and set them each to 0. Right? The sum of the total virtual work being 0 is the same as each component or each generalized force equal to 0. Okay, so that's all I had for today. Are there any questions? Was the audio much better, much worse than before? And was the handwriting any better? Thanks, Jason. The mic has its moments. All right. I'll try to see if I can find a better way to do the mic. All right. Thanks, everyone, for joining. Remember that the assignment is due on Friday, if you want to mark. But of course, you can have the option of having, the exam worth more. Yeah, I'm using a tablet, so that one has one input. So I have to see if I can use something that has, if the tablet can deal with, something that has both input one. All right, well, thanks, everyone. I will talk to you all on Monday.